Looks like you guys can. Okay. All right. Let's hope this works. Okay. All right. Let's see. All right. We're going to pass around a sign-in sheet. I didn't have today's attendance sheet for the SI today, so if you happen to be at SI today, please also sign in on the Wednesday part on this sign-in sheet. Otherwise, at least sign in on the exam review part of the sign-in sheet. And I know this room is big, so if you guys could pass it horizontally across the room, that'd be great. All right, 6:32. All right, so hopefully no one uses this room at 8:30. I don't imagine so. So if we go a little bit over, that should be fine. All right. So hopefully everything works. Okay. All right. So exam 2 is going to have chapter 13, enzyme kinetics. Chapter 13b or 15, if you look at the PowerPoint titles, that one will be about enzyme regulation. Chapter 7, A and 7b. 7a is monosaccharides and disaccharides. 7b is polysaccharides. 8a and 8b, which is like the same thing as 9. 8, oops, my bad. How come no one told me? That's your fault, not mine. Lipids and cell membrane. So plot twist, it's all written right here. Okay. So for those asking if 14.7 is on there or like 9.5 or whatever, I don't know. All I do know is in terms of PowerPoint titles, it's these 6 PowerPoints that you have on there. 13A, 13B, which also has 15 in it, 7A, 7B, 8A, 8B, and you're good. So today, because it's a 2-hour exam review, I will be covering the most important parts for each of these sections. So let's begin with enzyme kinetics. Okay. So, to begin with, for enzyme kinetics, you have to know all about Michaelis-Menten enzymes, which we'll break down right now. Okay. Michaelis-Menten enzymes are different than those allosterically regulated enzymes that you see in chapter 15. Michaelis-Menten enzymes are very simple. The basic theory behind it is this diagram right here. So obviously you guys should know that enzymes catalyze reactions and they speed up the rate of a reaction without actually altering anything with the starting point of the reaction or the ending point of the reaction. They just make it go faster. Now specifically Michaelis-Menten enzymes do this, and I'll attempt to draw this. You have an enzyme, you have a substrate, and what do they call this spot here on the enzyme? Active site, exactly right. This is where the substrate is going to bind to. Michaelis-Menten enzymes have only one active site. You can contrast that with allosterically regulated enzymes that are known to have multiple active sites. So Michaelis-Menten enzymes only have one. So the basic theory is that at the beginning there is an enzyme without anything bonded to it and a substrate floating around, and they come together to form this thing in the middle here called an enzyme substrate complex, which is an intermediate. The enzyme has the substrate bound to it, but doesn't automatically convert it into product. It needs to have enough energy, it needs to be the right conditions, whatever. Only in the right conditions is the enzyme able to convert the substrate into product, and we're left behind with the enzyme ready to go and grab another substrate and do the whole thing over again. So it's a very simple mechanism. What's important about this are the kinetics behind this. So I'm going to draw a graph. And you should be familiar with this graph in your notes in terms of SI practice. This is a graph of Michaelis-Menten enzyme kinetics. All this graph tells you is that on the y-axis it's the rate of the reaction, of the enzyme catalyzed reaction, and on the x-axis is the amount of substrate that is available, represented as substrate concentration. As substrate concentration increases, the rate of the reaction increases, but not infinitely, obviously. It reaches a kind of saturation point where the rate of the reaction flattens out here. That's because the enzyme isn't, infinitely fast. It reaches a maximum limit that it can handle, of which that limit is called Vmax, the maximum rate at which the enzyme can catalyze this total reaction. So Vmax is very simple. It's one of the two most important numbers you have to know about enzyme kinetics. The other one is called Km. Km, conceptually speaking, Km describes how well an enzyme binds its substrate. That may not be the scientifically exact definition. The reason why I say that is if you go look at the notes or the textbook, they say something like Km is a pseudo dissociation constant. So I'll put that here also for comparison's sake. Pseudo dissociation constant. But if you just read that, you may not realize what they're trying to say. So I simplify it as Km is just a number that describes how well an enzyme binds to its substrate. A low Km means tight binding. The enzyme is really good at grabbing onto its substrate. So the more efficient enzymes, the better catalyzing enzymes are the ones with low Km values. You won't be asked to calculate Km from this graph. Okay, so breathe a sigh of relief. What you will most likely be asked to do, and I will transition to the more important graph, is to analyze a Lineweaver-Burke plot, misspelling it here, is to analyze a Lineweaver-Burke plot where the y-axis is represented as 1 over the rate of the reaction, and the x-axis is represented as 1 over the substrate concentration. So it's literally the exact same information given up here, just everything is inverted. Mathematically, that turns this hyperbolic shape into a nice line shape, which allows us to calculate things a lot more easily. So this spot right here, your y-intercept, you should know, you should memorize and or internalize that the y-intercept is equal to 1 over Vmax. Whatever number you see there, you can plug in as your y-intercept and solve for Vmax very easily. Anyone want to tell me what the x-intercept equals? Exactly. So I'll write that down. X-intercept is equal to negative 1 over Km. So whatever negative x-intercept is there, you plug it in here. You can easily solve for Km to figure out Km and Vmax for this enzyme. If you want more details, obviously you can go back to the chapter 13 worksheets and the videos that are posted on there. But this is so far the bare basics that you really, really need to know for the exam. Let me give you a couple more bits of information. If you have multiple lines on a Lineweaver-Burke graph, I'll label this one A and this one B, you should be able to tell me which one is the more efficient one, which is the more efficient enzyme. Is it enzyme A or enzyme B? B. And the shortcut for that is whichever line is flattest, is going to be your more efficient enzyme. So look at B, it's a little bit closer to being even with the horizon there. B is going to be your more efficient enzyme. Another way of phrasing this is that A is the more inhibited enzyme. Okay, it's the same thing, right? A is a steeper one, so it's an enzyme that's doing really bad compared to B. You can actually say that A is an enzyme being inhibited compared to B. If you want specific types of inhibition, I'll get to it in a little bit, but this one here represents competitive inhibition. If A and B turn out to be the exact same enzyme, the line A is representing competitive inhibition, which I'll go over in detail in a second. But again, quick analysis if you're given a graph with multiple lines. The flattest one is the more efficient one, and the steeper one is the more inhibited or less efficient one. Okay.
Hey Josh.
Mm-hmm.
So if he gave us like the top graph and said like which one is more efficient, it would just be whichever one reaches Vmax first.
Yeah, he won't do that, but that's a good point, especially if it shows up on the MCAT or something. Yeah, the more efficient enzyme is easily found on this top graph by which one reaches Vmax first. And they could have different Vmaxes as well, but yeah, which one reaches its saturation point first would be the more efficient one.
Thank you.
Mm-hmm. Let's see, talk about that. Okay. A couple more bits of information that are critically important before we get into the inhibitor stuff. We talked about how to calculate Vmax using the graph and how to calculate Km using the graph. There's a couple other things you could potentially calculate, such as Kcat. Okay? If they give you the line of revert graph and one extra bit of information, which I'll tell you in a second, you should be able to calculate the Kcat. So Kcat is a number that describes how fast one of your enzymes operates. So Vmax is how fast all of your enzymes go, what the maximum speed is of all of your enzymes collectively go at. Kcat is the maximum speed of one of those enzymes. So mathematically, Kcat is equal to Vmax divided by the enzyme concentration, not the substrate concentration. So enzyme concentration would have to be given to you. You just do Vmax divided by enzyme concentration and you'll have a number for Kcat. Yes, you do need a calculator for this exam. It at least makes it a lot easier, not only for enzyme kinetics, but also for one other calculation question that's brand new this semester involving something called the Nernst equation, which I'll go over at the very end when we get to cell membrane stuff. But you will need a calculator. Like last time, it can only be a scientific calculator, so make sure you bring one. Other than Kcat, there's one other thing that you could possibly calculate, and that's catalytic efficiency, which there isn't really a symbol for. There's just a formula for it. Catalytic efficiency is how efficient an enzyme is. The more technical explanation is, at low substrate concentration, how well does your enzyme perform? It is mathematically calculated as Kcat divided by Km. Okay? So we can easily get Vmax and Km out of the graph. If we're given enzyme concentration, we can use the Vmax we got earlier to calculate Kcat. And since we have Km and Kcat now, we can also calculate catalytic efficiency. So these are the calculation formulas that are really the most important that you're going to need for the exam. There's another formula. You won't be asked to actually calculate anything with it, just to understand conceptually what it means. And that is this formula here. B equals max times substrate concentration over Km plus substrate concentration. If you see this formula, you should know that this is the formula applied to Michaelis-Menten enzymes. This is the formula describing Michaelis-Menten enzyme kinetics. That's it. This is not the formula used to describe allosteric enzymes. Allosteric enzymes, you don't have to know the formula for it either. But this formula is specifically for Michaelis-Menten enzymes. It does not describe allosteric enzymes. All right, let's talk about inhibition. I'm going to start a new page here. Enzyme inhibition. Let me make sure this is still recording. All right. So, enzyme inhibition. For this class, you only have to worry about, for Michaelis-Menten enzymes, you only have to worry about two types, competitive and non-competitive inhibition. And in fact, it's even easier than what I talked about at SI. Regarding competitive and non-competitive inhibition, you only have to know the conceptual parts, and graphically, you only have to know the Lineweaver-Burke part. You don't need to know the hyperbolic graph of inhibitors. So you only need to know the Lineweaver-Burke graph stuff, which you can simply memorize if you choose to. So, what does each one mean? So competitive inhibition goes like this. We have an enzyme. We have a substrate. In addition to this, we have an inhibitor, a competitive inhibitor, which shape-wise looks very similar to the substrate, but not exactly. So the shape of a competitive inhibitor, the structure of a competitive inhibitor looks very similar to the substrate. There's some consequences of that. Because it looks similar to the substrate, the competitive inhibitor is going to try to bind to the active site. It is competing with the substrate for the exact same spot on the enzyme. When it binds to the enzyme is unable to grab onto substrate and convert the substrate into product. So the rate of the reaction is decreased, and therefore you're inhibiting the enzyme. Mathematically, what this ends up doing is if you try to find Vmax of a competitively inhibited enzyme, you will find that it remains unchanged. Vmax does not change even though you are competitively inhibiting an enzyme. Km actually increases. So there's a reason why for each one of these. For the first reason, although you don't need to know what this looks like in the Michaelis-Menten graph form, I find it easier to explain why Vmax remains constant for competitive inhibition using this graph. So here's my illustration. Here's my regular enzyme with a regular Vmax. And this dotted line here is going to represent the exact same enzyme, but it is being competitively inhibited. Okay? The reason why that is, the reason why you see that this dotted line ends up catching up to the original enzyme is that when you flood an enzyme with substrate, with a bunch of substrate molecules, meaning you increase the substrate concentration to ridiculous amounts, you're going to overwhelm the competitive inhibitor. The competitive inhibitor is not going to be able to beat the substrate for the same active site because it is being overwhelmed by the number of substrate around. So a feature of competitive inhibition is that Vmax is actually the same as if it wasn't inhibited in the first place. And we can see graphically that is true, that if you just increase the substrate concentration enough, it's as if the enzyme wasn't inhibited at all. Now Km, I said earlier, was a number that describes how well an enzyme binds to its substrate. Because the competitive inhibitor is quite literally getting in the way of the enzyme's ability to bind to the substrate, it is making it harder for the enzyme to bind to the substrate. Therefore, Km increases. Remember, a higher Km is really bad. The enzyme has gotten worse at binding to the substrate. Okay? So let's contrast all of this with non-competitive inhibition. I'm going to have to redraw that because I didn't draw an allosteric site. Let's see. Substrate and a non-competitive inhibitor. Okay. So, with non-competitive inhibition, we have to worry about this other site on a Michaelis-Menten enzyme called an allosteric site. In this context, an allosteric site on the enzyme just means any site that isn't the active site. Okay? It is any site that the substrate will not go to. So for non-competitive inhibition, Instead of going to the active site, the non-competitive inhibitor is going to fit into the allosteric site. Because it's going to a completely different place, we can see that a non-competitive inhibitor has a shape completely different from the substrate. Okay, and that's intentional. That is so it only goes to the allosteric site, not the active site. What this ends up doing when the non-competitive inhibitor binds to the enzyme is it shuts it off. The enzyme is still able to grab onto substrate as if nothing happened. It just lost the ability to convert the substrate into product. Okay? If an enzyme is being non-competitively inhibited, it is still able to grab onto substrate. Because of that, Km is constant. The enzyme is still grabbing onto substrate as if everything's normal. But because it's turning the enzyme off, it is preventing it from being able to convert substrate into product. And this actually will affect the Vmax. Vmax will actually decrease when we're talking about an enzyme that is being non-competitively inhibited. So graphically speaking, again, I just personally find it easier to illustrate it this way. You won't need to know these graphs for competitive and non-competitive inhibitors. You need to know the Lyman-Revert graphs. Here's my regular enzyme. This time, for non-competitive inhibition, we very clearly have a lower Vmax. The line reaches a saturation point a lot sooner. It's a much lower Vmax in this case. And that's because enzymes are actually being turned off with non-competitive inhibition. With competitive inhibition, the competitive inhibitor is only binding temporarily. The competitive inhibitor up here binds to the active site, then falls off, and the enzyme can go grab substrate whenever it wants. Over here, though, functionally speaking, when a non-competitive inhibitor binds to an enzyme, it's turning it off. So that does affect the overall Vmax here. It doesn't matter how much substrate you add, it will not increase the maximum rate of the reaction. So, if you're wondering about Lyman-Revert graphs and stuff regarding these, I'm not going to go over the lengthy explanation for that. You can choose to either memorize what competitive inhibition looks like on the Lyman-Revert plot, or you can look at the videos I have for chapter 13, explaining how to figure out what the competitive and non-competitive inhibition looks like on a Lyman-Revert plot. I'm not going to go over it here. So, I'll say see notes for Lyman-Revert plot of inhibitors. You can choose to memorize it or conceptualize it. Okay, make sure I covered everything there. Okay, it turns out those are the most important things for chapter 13a. And so I'm going to move on to 13b/15 now. So enzyme kinetics, those are the most important concepts. Okay, so moving right along. Actually, I'll just start on the page. Chapter 13b/15. I didn't do a good job writing my notes here, so we'll be a little bit out of order, so forgive me. Probably the biggest concept in terms of amount of stuff you have to learn for chapter 15 is any information regarding glycogen phosphorylase. So I'll be jumping all around this section because as I've written my notes here, it is not exactly in order. It's more just how the topics show up. So, glycogen phosphorylase is a very unique enzyme. It is regulated via two different ways. Glycogen phosphorylase is regulated by covalent modification and allosteric regulation. Okay, so what does this enzyme do? The main job of glycogen phosphorylase is to begin the process of extracting glucose out of glycogen. You've gone through some chapter 7 stuff already, so you now know that glycogen is a polysaccharide composed of a bunch of glucoses. Glucose is the actual bit of monosaccharide that we begin to extract energy out of through glycolysis and citric acid cycle and everything. So if we want to actually get glucose out of glycogen, this is the very first enzyme that begins that process, and that is glycogen phosphorylase. So the substrate of glycogen phosphorylase is glycogen, all right? And it's going to attach a phosphate to it, and other enzymes will begin to rip glucose off of glycogen. So in terms of how it's regulated, you see somewhere in your notes, I hope, one of these pictures that kind of look like this. Probably looks a little bit more specific than this, but something of this shape. One of your two possible extra credit questions, and Dr. Hayes may have given you a third possible one, but historically speaking, one of your two possible extra credit questions is to explain in detail all this information about glycogen phosphorylase we're going to go over. How it's regulated, what enzymes may be involved, what effector molecules may be involved, how they positively or negatively regulate it, which version of glycogen phosphorylase is for homeostasis and which one's for emergency release of glucose, and finally, how does caffeine relate to glycogen phosphorylase, and how does diabetes relate to glycogen phosphorylase. All that information is given in your PowerPoint notes and in the SI videos that we've gone over before. So I'm going to break it down. First, I find it easier to describe how glycogen phosphorylase is regulated via covalent modification. And that's the horizontal part of this diagram. The horizontal part of this diagram is describing how this enzyme is regulated via covalent modification. So what covalent modification is pretty simple. It's covalent addition of some functional group to a target enzyme. In this case, the most common version of covalent modification is covalently attaching a phosphate group to an enzyme. This changes the activity state of the enzyme. Most of the time, covalently attaching a phosphate to something turns it on, really super activates it. But it's not 100% true all the time. There are examples of other enzymes where if you attach a phosphate to it, it actually turns it off. Specifically for glycogen phosphorylase, when you covalently attach a phosphate to it, you are super activating it. You are preparing it for emergency release of glucose from glycogen. You are preparing it for emergency release of glucose from glycogen. So everything on the right half here represents emergency release. Everything on the left half here, without a phosphate attached to it, is for homeostasis, normal, slow regulation of glycogen phosphorylase activity. So back up here, we're going to fill in some terms here. There are enzymes whose job is to attach phosphates and remove phosphates. Anyone tell me what the enzyme is that goes up here that attaches a phosphate to this thing? Kinase. Something kinase. I don't care about the long name. If you put down kinase, you're good. What is therefore the opposite enzyme here? Phosphatase, exactly. Phosphatase is the enzyme that catalyzes the reaction of removing the phosphate from the target enzyme. So there are enzymes that regulate other enzymes. In this example up here in the horizontal portion here, which describes covalent modification as a whole, a kinase enzyme is taking a phosphate from ATP, and sticking it onto glycogen phosphorylase to superactivate it. The opposite would be is if phosphatase comes in and removes a phosphate from glycogen phosphorylase, thus shifting it back over to the homeostasis side of this diagram. Okay, that is covalent modification. A couple other vocabulary terms to associate with covalent modification, and that is the phrase converter enzyme, which I guess I'll have to write up here. Converter enzyme. Your converter enzymes are the ones that are doing the modification. So your converter enzymes in this example here are your kinase and your phosphatase. They are the ones doing the modifications. The other vocab term to watch out for is the phrase interconvertible enzyme. The interconvertible enzyme is the one that is being modified, which in this drawn example here is glycogen phosphorylase. Shorthand notation GP for room here. So again, your converter enzymes are the ones doing the modifications, the ones attaching the phosphate, and the ones removing the phosphate. Your interconvertible enzyme is the one that is being modified, which in this example is glycogen phosphorylase. So that is the summary of covalent modification, yes?
So when you add the phosphate, you're basically making the relaxed state more relaxed, right?
It's a little bit more complicated than that, and I guess I'll talk about it now since we're about to talk about allosteric regulation. But what ends up happening when you covalently attach a phosphate to this thing is that it just makes it, this right half of the diagram, it makes the enzyme more greatly prefer the relaxed state. Not necessarily makes it more relaxed, it just makes the enzyme more greatly prefer the relaxed state, which I'll explain what that means in case you guys haven't studied the allosteric regulation stuff in detail. So, we've covered covalent modification. The next half of this is also just as important. It's the vertical portion of this diagram, which in your notes they write non-covalent, which doesn't really help much. The non-covalent part actually is the allosteric regulation part of this enzyme. So enzyme activities are regulated many different ways. Covalent modification was one way. The other way is via allosteric regulation, which if you look at the diagram, they label as non-covalent. It's the same thing in this context. So what allosteric regulation means is that you are no longer being asked to be regulated by covalently attaching stuff. What is now affecting enzyme activity is the presence of certain effector molecules. I'll plug in a couple and then I'll explain what they're doing. AMP is going to go there. ATP is going to go there. Glucose 6-phosphate, not going to have room for it, so you'll see it on the diagram. And caffeine. Okay? These are your effector molecules. Obviously, this is just my scratch work up here, but you guys have seen these diagrams in your notes, so please refer to them often. But what are these effector molecules even doing? Well, the core concept of allosteric regulation, the core concept of it, is that allosteric enzymes come in two types. A tense form up here, and a relaxed form down here. So allosteric enzymes come in two types, a tense form and a relaxed form. And there is an equilibrium between these two states, meaning depending on cellular conditions, the enzyme, the populations of this enzyme may shift into a more tense state or a more relaxed state depending on the presence of certain effectors and substrates. What does each one mean? The tense state of an allosteric enzyme is the inactive state. It's not going to catalyze any reactions. And the relaxed state of an allosteric enzyme is the active form of the enzyme. So in other words, these two forms down here are the ones actually catalyzing the glycogen phosphorylase reaction. They're actually grabbing onto glycogen and attaching a phosphate to it so it can proceed to, so that other enzymes can proceed to pull out glucose out of glycogen. So that's only these two states down here, okay? That's the relaxed form of this. Now, certain effector molecules are going to shift equilibrium from the tense state to the active state. Well, actually, in this example, there's only one, and that is AMP. AMP is an effector molecule that will shift equilibrium towards the relaxed form. It is, think of it as it's activating glycogen phosphorylase. And why is that? Well, this enzyme, if you think about metabolism as a whole, this enzyme is only needed when the cell is kind of in a starved state. If there isn't enough glucose in the cell, it's going to need to start looking for other sources. So it's going to find glycogen, and it's going to rip off glucose out of the glycogen to send it through glycolysis and the citric acid cycle. But how does it know when it's in a starved state? AMP is a very weak form of a nucleotide triphosphate. Remember, you've learned since Bio 1 that ATP is the energy currency in biology, right? That ATP is what is used to power practically every reaction that matters in a cell. So if there's an abundant amount of AMP floating around in the cell, it's a signal to glycogen phosphorylase saying we don't have a lot of energy, we need to start breaking down glucose wherever we can get it. So that is why AMP is activating this enzyme, because it's a signal saying we need to start pulling glucose from everywhere we can and start producing brand new ATP. The opposite, therefore, makes sense. That ATP right here is instead inhibiting this enzyme. If there's already plenty of ATP floating around the cell, why would you need to pull out any more glucose? You already have plenty of energy. It explains why ATP is an inhibitor of this enzyme. It is deactivating it. ATP is shifting equilibrium back up to the tense inactive form here. There's other stuff too. If glucose is already present, why would you need more glucose out of glycogen? I think that makes sense. That is why glucose is inhibiting this enzyme. Same thing with glucose 6-phosphate, which is just a different form of glucose that is very common inside cells. Turns out, a special bit of information here, that caffeine actually inhibits this enzyme as well. It turns out caffeine affects lots of different components of metabolism. In this context, caffeine is an inhibitor of this enzyme as well. It is a negative effector of this enzyme. It shifts equilibrium back up to the inactive state. Okay, so over here on the left describes your homeostatic regulation of glycogen phosphorylase, the slow way that things are regulated. AMP is present, it shifts it on. ATP and all this other stuff here shifts it off. That's the slow way. Now let's go back to this unique situation over here where we've covalently attached a phosphate to it. We still have allosteric regulation here, but in my opinion, the diagram doesn't do a good job of explaining what's going on the right side. In my opinion, I think a better illustration of this double arrow here, when there's a phosphate attached to it, is the following. Okay? It is a hugely different equilibrium than it was on the left side. On the left side, you kind of have a nice, like, even, sometimes it's active, sometimes it's inactive. Over here on the right, once you superactivated glycogen phosphorylase, by default, it will greatly prefer the relaxed form over the tense form. That's why I've drawn this longer arrow here to illustrate that. In fact, it so greatly performs the active form of the enzyme when it is covalently modified that there are no listed positive effectors here. You don't need any of them. You don't need anything to positively affect this enzyme because covalently modifying it has superactivated it already. Over here, there's a couple of inhibitors, and I may have them wrong. I always forget this part of the diagram, so please, when you're studying your notes, you can put the correct stuff here. I think it is glucose and caffeine, but I don't know. You can check there to see what the negative effectors are that belong here. All right, so in fact, I'll put a question mark here so that people are reminded to go check your notes to see what goes there. But it's the same reasoning in terms of effectors as it was over here on the left. These negative effectors exist to try to slow down this superactivated glycogen phosphorylase because you need to stop it at some point. So if there's already, again, plenty of glucose or caffeine happens to be around, it will try to shut off this enzyme. So this over here is for emergency release of glucose out of glycogen phosphorylase. There's a couple other things to talk about regarding glycogen phosphorylase, and that is how does caffeine and this enzyme relate to type 2 diabetes? You can find this in the caption for this diagram here, but think about it like this. Type 2 diabetes, one of the main characteristics of it is a high blood sugar, right? A high concentration of glucose in the blood. What caffeine does, as you can see here, is it's inhibiting glycogen phosphorylase. It is reducing the ability of glycogen phosphorylase to make more glucose, to begin the process of making more glucose. If it's preventing that mechanism of making more glucose, it seems like it's preventing mechanisms to have more glucose floating around in the bloodstream. Okay? So because it's preventing the production of glucose somewhat indirectly, that may be why caffeine is indirectly linked to a reduced incidence of type 2 diabetes. There isn't anything directly linked between the two, it's all just indirect information. But if this happens to be extra credit, just a small little sentence describing how caffeine is related to type 2 reduced incidence of type 2 diabetes is fine. You don't have to give me an explanation for it. Just stating that is enough for that component. Okay?
Can you repeat that real quick?
Question about the caffeine thing? Yeah. Caffeine is linked to a reduced incidence of type 2 diabetes. There's a bunch of theories